Okay, anybody have any homework questions you'd like me to do or talk about? All right. Well, we're getting into circular motion now. You've had a couple of lectures and a couple of problems, a few problems assigned. I'm going to give a quick summary of that, and then I'll do some new problems that you haven't seen. I just read this joke today, and it's not funny at all, but it is relevant to circular motion, so I'm going to tell it to you. Did you know that the inventor of the Ferris wheel and the merry-go-round never met each other? They travel in different circles. Okay, it's stupid. So that we can agree on, but here's why it's important. So if this is the ground, you know, and this is the sky, there really are only two types of circles that we're going to deal with in this class. There are circles that are oriented like this. That's a Ferris wheel. And there are circles that are oriented like this, and that's a merry-go-round. And at some point in every circular motion problem, you're going to have to use the fact that you're dealing with one or the other of these two things, okay? So be sure when a problem starts, you know which one of those two orientations you're dealing with. Those aren't the only two orientations you can have, obviously. Like you could have, you know, a circle going like this or whatever. We're just not going to do those calculations. So these are the only two cases you really have to consider, okay? All right, so circular motion, there's very little new that we haven't thought about when we talk about circular motion. There's two new names you have to get used to, and then there's one calculation you have to get used to, and that's all. So circular motion. Here's the new stuff. This really is all of the new stuff. Everything else you could derive from what you already know. The first one, in labs, we've been talking about this a-parallel thing that makes things change speed. In circular motion, a-parallel is called the tangential acceleration. So I'll always denote it as a vector A tan. Okay. You know, since it's an a-parallel, it only exists if the thing is changing speed. So, you know, it only exists if the object is changing speed. And if you have circular motion and the object is changing speed, that's called non-uniform circular motion. If an object is in circular motion and it's not changing speed, what's that called? Uniform circular motion, yep. So, and the uniform just refers to the speed. So if the speed doesn't change, it's uniform. Okay, so this one isn't too tricky. You just have to think the same way that you did about a-parallel, and if it's a circle, we call it tangential acceleration. The second one, a-perpendicular, that's always been the one that determines if something is turning. Well, in circular motion, the thing is always turning, and it's always turning in a certain way. So this is called, anyone remember what this is called? It's called centripetal. Centrifugal is another word, but it's actually has a kind of subtle, they're related, but centrifugal has sort of a subtle, sophisticated meaning that we're not talking about that. So be sure that in your head you remember this is centripetal, which means toward the center. And I'll denote that acen. And well, one thing that's interesting about circular motion is that this centripetal acceleration, this perpendicular acceleration, is always toward the center of the circle. Maybe that's not too surprising if you picture a circle, because the velocity is tangent to the circle. You know, picture a spot in a circle. I'm going to pick the bottom, okay? The velocity is tangent to the circle, so like this. The perpendicular acceleration is perpendicular to that, and so it's pretty intuitive that it's pointing toward the center of the circle, okay? And then the last new bit of information is that in circular motion, you can think of like, this is kind of what defines circular motion. We know the magnitude of that centripetal acceleration always. So the magnitude of a centripetal is always v squared over r, where v is the speed of the object, and r is the radius of the circle. And that's true whether it's uniform circular motion or non-uniform circular motion. We always know this about the centripetal acceleration. Okay, so just like any other kind of motion, the total acceleration is the sum of these parallel and perpendicular parts. It's the sum of the tangential and the centripetal. Okay, so given these three things, here is a set of steps that you can use for almost every circular motion problem, with the exception of one certain type. So here are general steps for circular motion problems except for what I'll call tetherball problems. For those type of problems where something's swinging around in a horizontal circle, like parallel to the ground, like a merry-go-round, and the only force applied, or the only contact that anything's making with it is a cable, there's an easier way to approach those. So you just have to remember that and remember to use a different approach for that. Everything else is going to follow this set of steps, okay? So the first one is choose a view of the problem where you can see the circular path. Or let's say where the path is visible as a circle. So that means if something is rotating in a circle that's parallel to the ground, like a merry-go-round, the view of the problem you want to take is from above, or it could be from below, but you need to be able to see the actual circle. You don't want to be looking at the side of the circle, you know what I mean? Second, you have to choose a single instant to analyze. We've always done that with free body diagrams and everything. We can only think about it at a single instant. Third, draw the vector A centripetal, draw the centripetal acceleration vector pointing from the object to the center of the circle. And the magnitude of that vector I'll call it like the centripetal acceleration without the vector sign. That's just the magnitude of that vector is equal to the speed squared divided by the radius. So far, everything has been the same, whether it's uniform or non-uniform. But this next step is only if it's non-uniform acceleration. If it's non-uniform acceleration, does that mean speeding up or slowing down? Or does that mean the speed is constant, non-uniform? That means the speed's changing, okay? So I'll put this in parentheses, step 4. So if it's non-uniform circular motion, then draw the vector A tan, that tangential acceleration vector, based on whether it's speeding up or slowing down, like we've been doing in our lab exercises for non-circular problems. Then step 5, there are a lot of steps. It might be a good idea when you're working on these problems to put a list of these steps out in front of you so you don't miss anything, until like after you've done a few problems, it'll, probably become sort of second nature, but for now, just have this sitting out in front of you. The total acceleration is just the sum of these two parts. And now once you've done that, draw a free body diagram of the object and use Newton's second law. So that 7-step process is just what you need to do on every one of these problems. So I'm just going to go through a couple examples. I'll go through at least one uniform circular motion problem and then a non-uniform too. Okay, so this first example, I once knew the name of this thing. I don't anymore, but you know, like in comedy movies about space, they always put people in those things that spin around and, you know, like to train you. Yeah, to train you for like high G forces, you know? Okay, well, that's the thing I'm talking about. We don't have to know the name, but that's what I'm talking about. So let's say we got one of those. Okay, so it's going around in a circle like this. Okay, and let's say that this distance is 4 meters. How fast should the astronaut go? You know, what should the speed be to reach 5 Gs of acceleration? Okay, so we're going to assume that this is uniform circular motion. We're not going to worry about the speed changing. We're going to assume that this thing, once it gets up to speed, it just stays at that speed. Okay, so uniform. And the first thing we have to do going through these steps is we have to choose a view for this problem where we can see the shape of the circle. So in this case, we need to think of looking at it from above. Okay, so there's the circular path. And this is the coordinate system we'll use. And this is, and then, you know, we have to choose an instant. So this is it. This is where the person is at the instant that we're going to do this calculation. Okay. Next, draw the centripetal acceleration going from the object, the person, toward the center of the circle. So there's the centripetal acceleration. And a centripetal is equal to speed squared, which we don't know yet, divided by the radius, which is 4. And so the acceleration vector, yes, question? Yeah, that's what this 4 is supposed to be. It goes from the center of that circle to where the person is. So the centripetal acceleration vector, notice that vector is in the positive x direction. Okay, so this is going to be v squared over v squared over 4 in the positive x direction and 0 in the y direction. This is uniform circular motion, so we don't have to worry about the tangential acceleration in this. It's 0, okay? And so the total acceleration vector is the centripetal plus the tangential, which is 0. So you just get back v squared over 4, 0. And for now, that's all we can say about the acceleration. We don't know anything about that speed. So now we'll go on to the next step, which is a free body diagram and Newton's second law. Well, let's see. So actually, almost always that's what we would do is a free body diagram and Newton's second law, but all we're asked for is we're asked about the acceleration, or the criterion that we want to satisfy is that the acceleration is equal to 5 times the acceleration of gravity. So 5 times little g really is 49.05. And we want to set 49.05 equal to the magnitude of our acceleration, which is v squared over 4. So v squared is equal to 196.2. Take the square root and you get v is equal to plus or minus 14.01 meters per second. This is the speed, so speeds have to be positive.
Right. So in the homework, if you ever get negative, it always just has to be positive.
Yeah, speeds always have to be positive. Yep. Any questions about that? Okay, so let's do another uniform circular motion problem. That one was fast. No, really just the speed does. I mean, everything that all the vector quantities we've been using, those can be positive or negative because that indicates the direction. But remember that speed is just like the magnitude of velocity, so that always has to be positive. Yeah, that's right. That's right. Okay, so now let's say that there's a 1,000 kilogram car moving around a circular track. And let's say that the radius of the track is 50 meters. And let's say that the car has a constant speed of 30 meters per second. So first, let's calculate the acceleration vector. And second, let's calculate the net force. That's the sum of all the forces acting on the car. It has a constant speed, so that means this is uniform circular motion. That means, again, we're not going to have to deal with the tangential acceleration, only centripetal. So just going through the steps. The first step is we have to choose a view where we can see the circle. So again, we're going to do this from above. And again, I'm going to orient my coordinate system like this. And then we have to choose an instant to look at. I guess I'm going to choose a different instant just so you get used to how these vectors work. Let's say that this is where the car is. And let's say that it's moving around this way. Okay. Now draw the centripetal acceleration vector. So draw the vector from the object to the center of the circle. And the magnitude of that is the speed squared divided by the radius of the track. The speed is 30 meters per second. The radius is 50 meters. And if you calculate that, you get 18 meters per second squared. Well, for the vector, for the centripetal acceleration vector, we want the magnitude of 18 pointing in the direction of that vector that we drew. That's in the positive y direction. So this is equal to 0, 18. Yep.
Placement of the car was like we had before.
Mm-hmm. Yes, that's right. And if it was over on the right side, it would be negative 18, 0. And if it was on top, it would be 0, negative 18. And those are the only 4 points you'll ever have to worry about. You're not going to have to use sine and cosine. You can maybe imagine like if it was over here, you'd have to use sine and cosine, but we're not going to do that. Okay, well, the total acceleration is the centripetal plus the tangential, and the tangential is 0 because this is uniform. So the total acceleration is just 0, 18. Then for part B, we want to calculate the net force. We're going to use Newton's second law, but if you're trying to calculate the net force, so if you're looking for F net, skip drawing the free body diagram. That's the only time that you have to skip it because F net is just lumping all the forces together anyways, so you don't care what those individual forces are. Okay. And so you can go straight in this case to Newton's second law, which just says F net is equal to the mass times the acceleration. So 1,000 times the vector 0, 18 And that gives you the vector 0, 18,000 newtons. Or another way you could think of that is the force vector is 18,000 newtons pointing in the positive y direction.
You just chose it as 1,000.
No, that was given in the problem. 1,000 kilogram car. Yeah, so the only time you don't draw it before you use Newton's second law is if it asks you about the net force, okay? Because the net force, the whole point of the free body diagram is you draw all the individual forces and then those all add up to F net. But if you don't care what the individual forces are, then the free body diagram doesn't help you anyways. You draw all these individual forces and then in Newton's second law, you just add them all together and make it F net in the first place. Anyways, you know. Yes, the next one, I'm going to do one like that, yeah. Any other questions about this? Okay, so now let's do a non-uniform problem. So this is something that our lab this week talks about. So let's say that you have a mass on a string and it's swinging around in a circle, okay? And this is like a vertical circle, like a Ferris wheel, okay? It's not parallel to the ground. And let's say that it's going this direction. And let's say that the mass of the ball is 0.1 kilograms. And the length of the string is 0.2 meters. And let's calculate two things. First, what's the, so let's say that we have some sensor attached to the string, and let's say that we know at this instant the string tension is 80 newtons. How fast is the ball moving at this instant? And then second, calculate the acceleration vector. Okay, so the first step is choose a view where you can see the circular path. And we're already told in this problem what location the object is that we care about. So we don't get to choose that this time, so it's over here. Draw the centripetal acceleration vector, so the vector from the object toward the center. This object is on the way up, so from lab, is that speeding up or slowing down? Slowing down. So if the velocity vector is this way, the tangential acceleration vector is this way. Remember, you can think about that exactly the same way as a parallel. Okay. All right, so now what do we know about the centripetal acceleration vector? Magnitude of that is the speed squared divided by the radius. We don't know the speed. We're going to have to calculate that eventually. Do we know the radius of the circle? Yes. So this is speed squared. The radius is the length of the string, so 0.2. And so I can write this as something divided by 0.2 is the same thing as 5 times the thing. And so what are the components of the centripetal acceleration vector? If this is the coordinate system, that centripetal acceleration is in the negative x direction. So this is negative 5v squared, and then 0 for y. And I've already drawn the tangential acceleration vector. We don't know, I'm going to take this off. We don't know what the magnitude is. We can't calculate that yet, but we know it's pointing in the negative y direction. So I'm going to write my tangential acceleration as 0, negative a tan. Okay. We just have to calculate that variable a tan to come up with that vector, you know. Well, this is as far as we can get right now for coming up with the parts of the acceleration. Let's put them together into the total acceleration. So A for now is negative 5v squared for x, negative a tangential for y. And we're going to have to come up with those variables v and a tangential in order to finish this vector, you know. Okay, well, now that we have what we know about the acceleration vector, I'm going to draw a free body diagram of the ball at this instant. So a free body diagram looks like this. Here's the ball. The weight acts down. That's 0.1 times 9.81, so 0.981. And then go around the boundary and look for contact. And the only contact with the outside world is the string. So what's the direction of that pulling force from that string? That is parallel to the cable, away from the chosen body, so it has to be this way. And I'll call that T. Now plug everything we know into Newton's second law. So the forces, we have negative T0, because this force is in the negative x direction. Plus 0, negative 0.981. Is equal to the mass times the acceleration vector. The mass is 0.1. The acceleration, as much as we know of it for now, is this. So negative 5 v squared, negative a tangential. That a tangential is just a variable. I could have called that a or x or p or whatever, you know. But we have to calculate the value of that variable in order to come up with this vector. Okay, so for part A now, the first thing is we know that that t value is 80 newtons, and we want to calculate how fast the ball is moving. We can get that from the x equation. It says negative t plus 0 is equal to 0.1 times negative 5v squared, so negative 0.5 v squared. And I'll substitute 80 in for t, so we have negative 80 plus 0 is equal to negative 0.5 v squared. And now you're just solving for v. So you get 160 is equal to v squared. Take the square root of both sides, and v is equal to plus or minus 12.65 meters per second. Capital V is a speed, so we'll take the positive one. Any questions about that? And the last thing we want to do is calculate the acceleration vector. This is how close we are to knowing the acceleration vector, right? This is the acceleration vector. We just didn't know v, or this variable a tangential. Now we know v, we just calculated it. So the last thing we have to do is get that variable a tangential. So I'm going to use the y equation. And it says 0 minus 0.981 is equal to 0.1 times negative a tangential. So a tangential is equal to 9.81. And now we have both of those two variables we needed. So plug those back into the total acceleration vector. And you get negative 5 times 12.65 squared for x, negative 9.81 for y, or negative 800, negative 9.81. And this is acceleration, so this is meters per second squared. Any questions about that? The last type of problem, the only type of problem that doesn't follow this approach, are problems where you're in a horizontal circle and the only contact is a cable or a string. Okay, so those are tetherball problems. I don't know why I call it that, tetherball. You know what tetherball is? I mean, it's like that. So we're talking about problems where it's a horizontal circle only supported by a cable. And the first thing you need to know about tetherball problems is, with the assumptions that we're making, those are always uniform circular motion. There can never be a speed change. There's no way to make the speed change in this scenario. Okay. So these are always uniform circular motion. That means that the tangential acceleration is always equal to 0. Okay, we never have to worry about that. So you have to, every time you look at a circular motion problem, ask yourself, is this a tetherball problem? If it's not, then you can go the other way, you know. But if it's a tetherball problem, then, excuse me, your first couple steps are going to be a little bit different. Okay. Really, the only thing that's different is the view that you're going to take to do the problem is different. So here are the steps that you'll follow for a tetherball problem. So first, take a side view of the problem. Okay, like if you were following the set of steps that I gave you for everything else, you'd be taking a view from above so you could see the whole circle. But this time you're going to be looking at it from the side. Okay. This is the only step that's new. And I'll just quick go through the other ones, but the other ones are the same. So in this side view now, you're going to draw the centripetal acceleration going from the object toward the center of the circle. Then you're going to, you know that the magnitude of that centripetal acceleration is equal to v squared over r. Fourth, you know the total acceleration is equal to the centripetal plus the tangential, always. But in this case, the tangential is 0. So the centripetal gives you your total acceleration. And then 5 and 6 are a free body diagram and Newton's second law. Okay, so let's say, for an example, we have a tetherball problem. This thing's swinging around in a circle like this. And let's say that this rope makes an angle of 30 degrees with the horizontal. And let's say that the mass is 1 kilogram. And the rope, the cable, has a length of 2 meters. And we want to know what are the tension in the cable, T, and the speed that the thing is moving. Okay. So first, if you saw this on a test or something, you'd say, okay, this is moving in a horizontal circle, supported only by a cable, so that's a tetherball problem. So I'm going to take a view from the side. Okay, so this is the view that we're going to take. Okay, and we know that this angle is 30 degrees. And you can draw your coordinate system. So I'll choose this one. It's hard to imagine anyone choosing a different one. Okay, now the centripetal acceleration. That goes from the object toward the center of the circle. So that's this way. Make sure that you see that makes sense, that that's the direction of the centripetal acceleration. So this is our centripetal acceleration. And the magnitude of that centripetal acceleration is v squared divided by the radius. What's the radius of this circle? So on these, you have to be a little careful. The radius is actually this. You see that? And so you have to use, well, you're going to calculate that as this is equal to the length times the cosine of that angle. So in this case, that's equal to, 2 times cosine of 30, which is 1.732 meters. So the centripetal acceleration is v squared over 1.732. We know it's pointed in the negative x direction. So the centripetal acceleration, which, since this is uniform circular motion, is just equal to the total acceleration, is negative v squared over 1.732, and then 0 for y. We don't know v yet. We can't find it without using Newton's second law. So now we're going to go to the free body diagram and Newton's second law. So the free body diagram, there's the ball. The weight is acting down. That's 1 times 9.81, so just 9.81 newtons. And the only other force that's acting on the boundary is from that cable. So that pulling force has to be parallel to the cable, away from the chosen body. Okay. Well, we're going to have to represent this cable force as a vector for Newton's second law. So let's just do that now. So if this is our coordinate system, and this is the vector, it has a magnitude of t. What's the counter? And we know that this angle is 30. What's the counterclockwise angle from the positive x-axis to this vector? 150, yep. So this vector is going to be t times cosine of 150, t times sine of 150. And that comes out to be 0.866 t negative, and then positive 0.5 t. So now we'll put everything in Newton's second law. We have these two forces, the one we just figured out. So negative 0.866 t, positive 0.5 t, plus the weight force, which is 0, negative 9.81. Is equal to the mass times its acceleration. And its acceleration is negative v squared over 1.732, and then 0 for y. So we get two equations. The x equation says negative 0.866 t is equal to negative v squared over 1.732. And the y equation says 0.5 t minus 9.81 is equal to 0. So we have two equations with two variables in them. In this case, we're going to solve the y equation for t and then plug that in to the x equation. You see that? So this multiply both, let's see. So 0.5 t is equal to 9.81. Multiply both sides by 2, and you get that t is equal to 19.62. And then plug that into the x equation, and you get negative 0.866 times t is 19.62. Is equal to negative v squared over 1.732. So v squared is equal to 29.43. And so v is the square root of that. So v is plus or minus 5.42 meters per second. V is a speed, so we'll take the positive one. Any questions about that? What's the deal with this angle? So that angle with the horizontal was 30 degrees. If that string was closer to hanging straight down, so that would make that angle bigger, right? So say that angle was 80 degrees. Do you think this speed would be higher or lower? And do you think that tension would be higher or lower? That's right. That's right. So that speed would be lower because it's the speed that, like if you played tetherball, like the harder you whack it, the more closer to horizontal that string goes. So the faster it's going, the closer to horizontal the string will be. And then we know from Newton's second law that the faster that speed is, the higher the tension force is going to be. So making that speed lower is also going to make the force lower, the cable force lower. Do you think that string could ever be perfectly horizontal? Well, let's just do one more quick calculation, okay? Let's do the same thing. But let's say, what speed would be required for that angle to be equal to 89.9 degrees? No, sorry, 0.1 degrees. We want it closer to horizontal. Okay, so that means that this thing is 1/10 of a degree from being perfectly horizontal. And let's see what speed is required. It's going to be a higher speed, right, and a higher tension. Well, what's going to change? The centripetal acceleration I guess let's just go through the whole thing again quick. I won't belabor everything as much, but so we're looking from the side and there's the object, and even that's exaggerated, but that's the cable, and then this is the radius. Okay, so this is R. This angle is 0.1 degrees. The centripetal acceleration is this direction. And it's equal to v squared. The magnitude of this is equal to v squared over r. And r is equal to 2 times the cosine of 0.1 degrees. Which is almost exactly 2, because that's such a small angle. And so this centripetal acceleration is v squared over 2. So the centripetal acceleration vector is negative v squared over 2, and then 0 for y. The free body diagram There's a weight force down of 9.81. There's a cable tension that's almost horizontal, but not quite. And so that cable force is going to be T times cosine of 179.9 T times sine of 179.9 which is like almost exactly negative T for X. And then for Y, it's positive 0.00175 T. So Newton's second law, we have this force vector from the cable, negative T, positive 0.00175 T, plus 0, negative 9.81, is equal to the mass times the acceleration, which was negative v squared over 2 for x, 0 for y. So now we have two equations. Negative t is equal to negative v squared over 2. And the y equation says 0.00175 t is equal to 9.81. So you get that t is equal to 5,620.72 newtons. Now plug that into the x equation, and you get negative 5620.72 is equal to negative v squared over 2 and so v is plus or minus 106.03 meters per second. We want the positive one. So to get that cable angle to be 30 degrees from horizontal, required that thing going about 10 miles an hour. To get it going a tenth of a degree from horizontal requires about like 230 miles an hour, you know. And the faster you go, the closer it gets to horizontal, but it would never get there. It can't ever get all the way horizontal. Any questions about that? Okay, that's all for today.